Okay, so so far we have looked at one type of cascade prediction model, cascade growth model, which was decision based model. Now we will look at another type of models called probabilistic cascade model. So what's the problem? So we discussed in the last lecture what are the major problems in cascade decision based cascade model. The first problem was that you know, the real contagion, right? For example, real epidemic spreading is not as simple as a decision based model that you decide whether you will be infected or not and then you get infected, right? It is more complex and this is more of an unobserved event, right? So, and a lot of randomness is involved in this process. So when we talk about you know, a contagion spread, right, we generally look at this kind of structure. We already mentioned, say this is the node, and let's say the node has 3 neighbors. Out of these 3 neighbors, all these 3 neighbors have come in close contact with this guy, but only these 2 neighbors have got infected. Similarly, right, similarly, say each of these neighbors again has 3 neighbors and only some of them have got infected, right, and so on and so forth. So from this tree like structure, you can basically get a filtered tree like this, okay, based on only the nodes which have got infected, okay, like this, right. So our task would be to understand whether this kind of spread will go on and on, right, whether they will stop eventually or it will not stop, okay. So to understand this, we basically use a setting which is called a random tree, right. What is a random tree? A random tree is a tree like structure where and the depth is infinite depth, and we assume that each node has same number of neighbors, right. So in this case we assume that each node has 4 neighbors, d equals to 4. So we assume a denary tree, right. Each node has d neighbors, and we also assume that the first node, the root node, has already got infected, and the probability that a person will infect another person is basically q, right. So with probability q, this guy will infect this guy, with probability q, this guy will infect this guy, and so on and so forth. So with 1 minus q probability, the neighbor will not be infected, okay. And what we are interested in understanding is that for which value of this d and q, right, the virus will spread, this spreading process will go on and on, the epidemic will last forever, okay. So that's the probability that we will try to measure in terms of q and d, right. So essentially if you look at this depth, right, depth h, right, h equals to 0, h equals to 1 and so on, at every depth if at least one node gets infected, then it means that this cascade will go on and on, right. So we will measure that what is the probability that at least one node gets infected at depth h, okay, and in the limiting condition h would tend to infinity. So we will basically measure this probability. As h tends to infinity, what is the probability that at least one node at depth h will be infected, okay. So what is the probability? What is the case? Wow, I mean, what is the chance that this probability would be greater than 0 as h tends to infinity? If it is greater than 0, then the epidemic will go on and on, right. and if it is 0 in the asymptotic limit, then it will stop eventually. The epidemic will stop eventually, right? So we will calculate this probability. All right. So let us try to understand. So each node has d children, right? And the probability that that say this is h minus 1th depth and this is hth depth, okay, and we will measure this pH, the probability that at least one node is infected at depth h, at least one node. How do you calculate it? So what is pH minus 1? pH minus 1 is the probability that at least one node is infected at depth h minus 1. Let us say this is the node, okay. So this node will infect each of its neighbors with probability q. So with probability q, it will infect one of its neighbors. So q times pH minus 1 is the probability that at depth h minus 1 there is at least one infected node, and depth h that infected node will infect another node with probability q. What is 1 minus this? This is the probability that that node, say I am talking about this node will not be infected, okay, to the power d. That is, so this quantity is none of these d neighbors will be infected. 1 minus this is the probability that at least one neighbor will get infected. So this is kind of an OR function. We discussed similar kind of functions where, if you remember, we discussed this thing in the big clam formulation in the link prediction chapter, okay. So this probability is basically indicating that at depth h at least one node will be infected due to at least one node which has got infected at depth h minus 1, okay. Now, so how do we, this is kind of a recursive function you see here, right, because in the next stage we will use it to calculate p of h plus 1. So now how do we solve this problem? So if you think of it carefully, this is essentially f of x equals to 1 minus right, say f of so you start from this root node and this root node is already infected, so the probability is 1. So then you put 1 here, this is your f1, this would give x1. In the next iteration you put f of x1, you will get x2, and so on and so forth, right, and so on and so forth. So this we need to now calculate. So let me erase it, or let me see. All right, so f of x is 1 minus 1 minus q times x to the power t. How do you solve this? Okay, this is so there is no closed form solution, right? So how do we solve this? We discussed in the network growth model chapter, right, Barabasi-Albert model, right, that we use it in a graphical form, okay. So there are essentially two things. One is y equals to x, and the other is whatever, right, fx is this one, okay. So this is y equals to x curve, this is x and this is fx, Okay, and let us assume that this curve looks like this. Okay, what is x? X is the probability, ranges between 0 to 1. Okay, so this is 1. Okay, what would be f1? If we look at it here, this is 1. f1 would be this one. This is f1. So now f1 is x1, right? So in the next stage, f of x1, right? So f of x1 would be, say this is your value, right? This is x1. I look at here x1. So this is the same length, okay? x1 and corresponding value. This one would be this one, say for example, right? Similarly, the next one would be x2 and so on and so forth. Okay, so we will keep on doing things, this thing until unless we reach here, this point. What does this point indicate? At this point, fx intersects y equals to x. What does it indicate? It indicates that so say this is x2, right? So f of x2, you get x2, okay, and you get x2. You again put the same value within f, you get x2 and so on and so forth. So you kind of get stuck, okay. So you kind of get stuck if you intersect at this point, right? But if you intersect at this point, and what is this? This is x equals to 0, right? And that would be your solution. You basically want that, you know, that this probability value pH, right, would tend to 0 for the epidemic to die out, right? So what would be your target? Your target would be to come up with a function which would look like this. It would only intersect at x equals to 0. Okay, so let's try to understand the behavior of this particular curve. Okay, so let's look at it. So f of 0, I'm trying to understand because I drew this curve randomly. Now let's try to understand the shape of this curve. So f of 0 is 0, right? Because this would be 0, this would be 1, 1 minus 1 is 0. F of 1 would be 1 minus q to the power d at x equals to 1, right? Now think about it. What is q? Q is the probability. So 1 minus q would be less than 1, right? To the power d would be less than 1. So this would be less than 1. 1 minus this would be less than 1. So this would be less than 1, right? Now let's take the derivative. F dash x, this would be d times right. What is f dash 0? This is at x equals to 0. This would be q times d. Okay. So now let's see. Let's look at this one. So if x is greater than 0, right, or greater than equals to 1, right, So what is x? X is the first probability, right? From where you started, right? And then you get this one, then it will again come here and so on. So x is also probability, right? So x ranges between 0 to 1. Q also is a probability. Q ranges between 0 to 1. So this would be less than 1, right? 1 minus this, of course I am not considering the case when both x and q would be 0, okay? It is greater than 0. So 1 minus this would be less than 1. This to the power d minus 1 would be less than 1 but greater than 0, right? So the entire thing would be greater than 0. So this would be greater than 0, okay? So if the derivative is greater than 0, then this function is monotone. So f of x is monotone as f dash x is greater than 0, right? Yeah, that is sufficient to show that this is monotone, okay? Within the entire range of x, okay? So it is monotone, right? Now let's see what is the other property. So f dash x is also non-increasing. What does it mean? Say, look at this one, okay? Say x equals to, with the increase of x, so let's say x equals to 0.5 and x equals to 0.9, okay? X equals to 0.5 and let's say q equals to some number, okay? Let's say q equals to 0.5, okay? So when x equals to 0.5 and q equals to 0.5, this would be 0.25, okay? 1 minus this would be 0.75, right? And when x equals to 0.9, this would be 0.45, right? And this would be 0.45 and this would be 0.55. So as x increases, this will decrease, which is very obvious. So this is non-increasing. So the derivative, the slope is non-increasing, okay? So the slope is non-increasing and the slope is also monotone. So you can expect like this. Right? But it may also look like this. So what is the condition by which we can say that this curve would be below this point, would be below this one? Okay? What is the condition? The condition would be at f dash 0 at this point, right? The slope should be less than 1. Think about it. At this point, the slope of y equals to x is 1. The slope of any line or any curve above this would be greater than 1. And the slope of any point would be less than 1. I mean any line which is below y equals to x would be less than 1, the slope. So at 0, the slope is q times d. So q times d would be less than 1 in order to draw this kind of curve which will intersect only at this point, right? And what is this q times d? Think about it. It's very simple notation. D is the number of neighbors and q is basically the infection rate, right? So this is expected number of neighbors which or who will be infected. If this number is less than 1, then the epidemic will die out. Okay. Now this number Q times D, this is called R0. Okay. So this is called reproductive number. This is called reproductive number. So for any epidemic, this reproductive number should be less than 1 in order, and you can basically come up with policy strategies so that this would eventually be less than 1 so that it would die out. Okay. All right. So let's look at an example case, right? So, and if you actually tally, right, if you look at the real world cases, this R0 value for HIV was around 2 to 5. Says for measles, for measles, R0 was between 12 to 18. Think about the amount of infectiousness, right? For Ebola, it was around 1.5 to 2. These are all scientifically shown. Okay. So if you look at a real world online activity, right, online spread, there is a nice paper, okay, of this, that paper was published in ACM WSN conference, Washington conference in 2008, which basically looked at how images on Flickr. So Flickr is a famous online media site to upload images, right, photos. How photos spread on social media, right, and can we correlate and can we come up with a reproductive number for this kind of spread of photo sharing behavior on social media? And what they did, they calculated the empirical reproduction number, right, empirically, right. So empirically, how can you do? So for every node, you basically look at how many neighbors are infected and so on and so forth, and you get an estimation using the theoretical value R0, which is Q times D, right. And it turned out that the correlation is really quite high, 0.97, right. You see that, and all these points, right, this cross points, these are different data points, and you feed a line and you see that the correlation is quite high, 0.97. Okay. However, they used this formula, they used R0 as Q times D times some factor. So this factor basically takes care of the skewed nature of degree distribution, the cascade distribution. This is not that important, but they basically took into account this Q times D factor to calculate the estimated value of R0. Okay. So we stop here. In the next lecture, we will discuss about some other epidemic models, SIR model, SIS model, this kind of models, which are primarily taken from standard biological epidemic, standard epidemic growth model, and those models are quite dated, because but those models are quite important, because whenever you try to come up with a new model for capturing the spread of any disease, right, any epidemic, we start off by using those models and then we come up with sophisticated ways. Okay. So we'll discuss those models in the next lecture. Thank you.